Hi, my name is Adrian O'Sullivan. I'm a PhD student in UCC. I'm under MARI and getting funded by the SFI. My PhD is based on control engineering with wave energy, and hopefully in the future it'll be about wave energy devices in array formats. This video is about my paper, Wave to Wire Power Maximization from a Wave Energy Converter, where this is one of many videos about this paper, and this video is about Model Predictive Control, and it's the second part, where this part goes into the prediction matrices and how we put those matrices or those predicted values and use them in the cost function. This is the second video. The first video goes into the zero order hold, the first order hold, and how exactly you got those models. But this goes and explains more about the prediction values. So this is the cost function that we saw in the previous video, and it's just a summation of the scaled PTO force, where this is the zero order hold version. Okay. So what we're trying to do is, let's see here right now. So just an example here, let's take the first step, the first sample. So it'd be UD of K, and then the next one would be UDK plus 1, and it goes all the way up to N. So what we have to do is trying to represent just this value here. And this goes all the way up to N, sorry. And then what we have to do is try and represent this into the cost function form in a matrix form. So we have to get this multiplication here into a matrix form, represented by just the outputs of the system, which are Z of K, Z dot of K, and UD of K minus 1, and delta Z dot of K. So how do we get this? So we get a UD of K, so we have to go one step into the future, and you see here that we get all the values that we need to complete this objective. So to get I equal to 1, 2, 3, all the way up to N, we have to predict the values of YZ K plus 1 all the way up to K plus N. So how do we get this into the matrix form, where you have just in terms of the output of the system and a symmetrical matrix in the middle? We put it into this form, where we have the output matrix transposed against a matrix which I like to call M, multiplied by the outputs to that system again. So you see here that this matrix here is the output transposed at position K plus 1, and the MZ, and then YZ K plus 1, where these are the exact same. You can lay it out and it'll be the exact same. So what is the cost function when you combine I equal to 1 all the way up to N, which is all the values of the receding order? You get YZ hat, which is equal to an array of all the receding order values, and then you get Q, which is a diagonal matrix which is multiplied by the MZ. So it's just adding up all the multiplications of every step all the way up to N. Where this, well, how do we get these values, the predicted values? We know that the state space system is the standard one. And we also know the output of the system. So how do we get yz of k plus 1? Well, you just put it one step into the future, and we already know what xz of k plus 1 is. So we fill that in. And you can see here that yz k plus 1 is in terms of all the present terms, and it's in terms of the state we have at that instantaneous moment and the values which we must predict, which are the excitation forces, delta z, or delta v, sorry, and the predicted PTO forces. So this is yzk plus 2, and it's just doing the exact same thing, and then you fill into xzk plus 1, but I didn't do it there because you can go all the way down to n and it's a bit awkward. So by doing this n times, it'll be possible to put this into matrix form, which is it's a lot easier to look at, and it will look like this. So we have the array of predicted outputs, which is yz hat of k, and then this goes all the way down to az to the power of n. And then this matrix here is called the Hessian matrix, or a diagonal matrix, or a lower triangle matrix, I think it's called. I ran out of space here now, so I gotta just push it up to the top. And that's all multiplied by the predicted PTO forces that we want to calculate. So the first one would be delta uz of k, all the way down to delta uz of k plus 1 minus 1, which are n predicted PTO forces. To continue this, we just add on the disturbance Hessian, which is the exact same, but instead of CZ by BZ, we get CZ by FZ. Whoops. So it is the exact same. And then we have the predicted excitation force values, which do need to be predicted. In my work, I didn't actually, I assumed that I knew those values, but there's been some great work out there that have great papers on, or people have done great papers on prediction values. With these predictions, we can then put them into that matrix form of the cost function that I showed earlier on. But first, we had to kind of simplify that the big matrix form that we just did there. So we have P is equal to the CZ by AZ all the way down to AZ by the power of n. The HA is the first Hessian matrix, which is to do with the PTO forces, and then HW is exactly the same as the PTO force Hessian, except it's in terms of F as Z instead of BZ. We can then put this into the cost function in the matrix form, as I was just saying earlier on there now, which is JZ of K. Q. And we have to do this because there are some terms in this equation that don't depend on the delta UZ hat values, which means that the cost function, there's a part in the cost function that has absolutely nothing to do with the PTO force, so there's nothing we can do about that. So when, let's just say there's no constraints to get the maximum or to get the minimum value, you differentiate it in terms of delta U hat, so that goes to 0 anyway, so we can neglect that at the end, but I'll show you at the end. So here we got the y hat values and the y hat transpose values. So then when we fill into the cost function matrix form that I just showed there, you get this value here. This goes on for ages here, but I've done it in different colors, so hopefully you can follow. So the first color is, yeah, so this part here is the y transpose by q, and then the yz of k. So this part's fairly tedious, but it's grand, yeah. So I sectioned everything off, color coded it. So sorry for people who are colorblind, but it's very hard to do it without kind of. It's just handy doing it with colors anyway. I couldn't do it with numbers because there's going to be numbers left, right, and center here. So the green is to do with the. You can see here the first few terms, which is x transpose by pt transpose or p transpose. The next terms in blue start with delta u of z transpose by HA transpose. Running out of space. And then the next one is delta U, or sorry, delta VZ hat transpose by HW transpose. So they're just the starting values, you can see them there. Just to finish it off here. So as I was just saying there, before I even started this calculation, just a few slides ago, anything to do that's not in terms of delta UZ of k can be neglected, because when you differentiate it to get the minimum value, those values go to 0 anyway. So we can get rid of this value here. That's grand. This value here, this value here, and this value here. So they all go to 0. So this is the new cost function. So these were left in because, as you can see here, I'm underlining it, there's the delta UZ hat values. So for this part, you'd really have to just plot out the dimensions of the matrices if you don't believe it, but this value here is equal to the transpose of that value, because it's a symmetrical value, because it's just one single value. It's a 1-by-1 matrix essentially. And then it's the same with this one here. So then when we decide to fill these two back into that new cost function, to make it more convenient, I chose the matrices, or the matrix groups where you have the delta U of Z hat on the right side. You can do it on the left side with the transpose side, but it's nicer to see it on the right side without the transpose. So when we fill back in, we get this. And then we can cancel out the 2's here and put it all in terms of the delta uz hat of k values. So everything inside this square bracket, that's going to be a constant, because you should be able to know the excitation predictions and also the states. But you don't know what delta u of z is, obviously, because that's what you're trying to optimize the whole thing for. That was all for a zero order hold MPC. The first order hold is basically the same, but there's a few changes here and there, and I'll go quickly through them here. So the first order hold MPC is basically the same as the zero order hold version. The most obvious thing about it is that the new Q matrix is a lot smaller than the Q matrix of the zero order hold, because there's one less state to deal with. So the MF matrix, or the MZs that you had in the zero order hold version, it's going to be a 3x3 instead of a 4x4. So the QF matrix is going to be a lot smaller. And then this last value is MF over 2, because it's the trapezoidal method. And if you included the start of the trapezoidal method in the last video, you would have an MF over 2 at the start on the top left of the QF matrix. So if you put that value into that array of output values, it would be wrong. Or you could put it in, but it would be completely irrelevant, because these values that you have here in your output is absolutely nothing. It can change nothing about your prediction values, because they're values that you already know. So there's nothing to predict, essentially. So this is the new MF matrix. And then the predicted PTO force array starts with delta UF of k plus 1, where with the zero order hold at k plus 1, k plus 2, the value that you're trying to calculate is the delta u z of k, and you'd have another value up here. But with the first order hold, let's just take a few points here now. Hopefully I can get this across. You take a few points here, and these are linear lines, because the first order hold is linear or piecewise linear. So the value you're trying to calculate is delta u of f k plus 1. So it's the change of PTO force between k and k plus 1 that you're trying to figure out. You already know the value at uf of k, and you're trying to get the value that you want to change to of uk plus 1. But for the zero order hold, you don't know what the value is at uz of k, because it's an instantaneous change. And that's why you calculate out those values, or they're shifted one step into the future for the first order hold. So that's it. Thanks for watching. If there's any questions, please leave some below. And hopefully I explained myself well, and if I didn't, just leave a few questions. Thanks.